Hello everyone and welcome back. So this time we have a pendulum and it consists of a 30-pound sphere and a 10-pound slender rod. So I'm giving you a composite body this time. And once again we have some random string or rope that snaps. So what are you going to try to find? We're going to try to find the reaction at the pin O right here, just after the chord AB is cut. So it gets cut, it's going to begin falling, but it hasn't moved anywhere yet because it's just instantaneously afterwards. What's your plan? Well, just the same thing as always. Draw your free body diagram, get a kinetic diagram, and you're going to have to figure out how to get the mass moment of inertia for this composite body. So go forth right now, try it out on your own, and see how it goes. And if you get stuck, you just come back, watch the rest of the video, and we'll do it together. So 3, 2, 1, and we're back. Let's try it out together. Now, if you look right here, what we see is we've got a free body diagram. We have the weight of the sphere, we have the weight of the rod, and we have these reaction forces. Now, the weight of the sphere and the rod are going to cause an acceleration. Interesting thing, though, is that there's going to be an acceleration for the sphere and an acceleration for the rod. And they're going to have the same angular acceleration, but will they have the same linear acceleration? Well, in the normal direction, yes, because that's going to be 0. But what about in the tangential direction? Well, that should be kind of easy to see here. That that sphere weighs more, has a bigger mass, and it's further down. And if they have the same angular acceleration, well, guess what? It's going to have a greater tangential component to the acceleration for that sphere than for the rod. Now, with all of that in there, we can plug everything into our equations of motion. So first off, in the x direction, we see that there is no acceleration in the x direction. So some of the forces in the x direction, or the normal direction are 0. And therefore, my pin reaction in the normal direction, or the x direction, is going to be 0. If I look in the tangential direction, I do see forces. We have our weights acting there, and we have that tangential component of the reaction force, which is in the y direction. And it's going to cause an acceleration of the sphere and the rod. Be very careful here, though, because it gives you the weight in pounds, and you would need the mass, which is in slugs. So you have to divide by 32.2. Do not forget that. It will throw you off. When I simplify, I can get an equation for the pin reaction in the y direction, or the tangential direction, and the angular acceleration. So I use my third equation, which is going to be some of the moments around our point O. And this is a bit of a longer one. So the weight of the sphere and the weight of the rod, they're causing the moment. But then their mass moment of inertia is kind of crazy. It's not terrible, but it looks pretty hard. So what am I dealing with here? Well, first off, you see this 0.4 times 30 over 32.2 times 1 squared. So what is this? What is going on here? Well, we've got to think about it a little bit. Okay, so if we look at this equation is just taken from the inside of your textbook. That's the mass moment of inertia for a sphere. It's the mass right here times the radius squared times 2/5. And then the rest of it is simply our mass, once again, times the distance from the centroid of my sphere to wherever we are. This is the parallel axis theorem. And we do the same thing for our slender rod, but this time we have a slender rod, so it's 1/12 times its mass times its length squared, and then the parallel axis theorem. So there's a lot of writing there, a lot of work, but it's just taking the mass moment of inertia of this and the mass moment of inertia of that, adding it all together and multiplying it by the angular acceleration. So with that, we can solve for the angular acceleration, and it comes out to be 10.9 radians per second squared. And then our reaction force in the y direction, or the tangential direction, if you want to call it that, is going to be 6.14 pounds. So that's it for this time. Thank you so much for listening. I hope this helps you, and I'll see you all later. Bye-bye.